In this video, we're going to take a look at goodness of fit test for a geometric distribution. So to start off with then, you should be aware of the conditions under which a geometric distribution is likely to arise. So as you can see here, these are the four key conditions under which a geometric distribution is likely to arise. So what do we have here? Well, to start off with then, we say that the trials are performed until the first success. So that's kind of the key idea there behind the geometric distribution. We then say that the probability of success is constant. So remember, this is our parameter then for the geometric distribution P here. That is the probability of success. We then say that the trials are independent. And then finally, the trials have two outcomes, success and failure. So that would be P, that would be 1 minus P. Okay. And you should also know the following probability for a geometric distribution. So this is the probability mass function then for a geometric distribution. And don't forget, this result is given in the formula, but just in case you can't remember this. Okay. So the probability that our random variable x here is equal to some value, let's call that r. Well, that is equal to P times 1 minus P to the power of r minus 1 there. And let's say we take a sample of size n from a geometrically distributed random variable, let's call that x here. Then the expected frequency of observations of the value r is given by the following result here. So as you can see then, this is equal to n times our probability mass function here. So n times the probability that our random variable x here is equal to some value r, which is equal to P times 1 minus P to the power of r minus 1. And again, this result should hopefully be very much familiar to you. This is just what we have for the geometric distribution here. Okay, the PMF for a geometric distribution, I should say. And then finally here to finish with, for a geometric distribution, we have one parameter. We already mentioned that here in our conditions, then that's the parameter P here. So we have one parameter P, and this can be estimated using the following result here. So as you can see then, P is equal to the total number of successes divided by the total number of trials. So that's equal to n divided by sigma r times f of r here, okay, or f subscript r. So you do also need to be aware that you sometimes may have to estimate the parameter P here, and this is how we do it, okay? So we've already seen a lot of goodness of fit tests here. So the idea of goodness of fit test and hypothesis testing at this point now should be pretty much trivial. All we're doing now is applying this to a geometric distribution, okay? So please do make a note of the following kind of lines here and key bits of information, especially this very final point here about how we estimate the parameter P. But that actually gives us everything that we need here then for our introduction to goodness of fit test for a geometric distribution. Let's just take a look now at one practice question. Let's take a look then at this practice question here. So what do we have for this practice question? Well, we're told that the table below shows observed values for what is thought to be a geometric distribution with parameter P being equal to 0.7. Okay. And we can see the table here below showing our observed values. So this question asks us to calculate the expected frequencies and using a 5% level of significance to conduct a goodness of fit test. So where do we begin here? Well, given that we're hypothesis testing, a good place to start is to define our hypotheses here. So we need H0 and H1 here. So for H0 then, what do we have here? Well, let's choose a random variable to model this situation. So if I choose x here, so x will follow a geometric distribution. So a geometric distribution here, and my parameter then is P being equal to 0.7. Okay. So what I'm saying then for H0 here is this distribution is a suitable model. So let's just write that down. So x following a geometric distribution with parameter 0.7 here is a suitable model. So this is a suitable model. And then for H1 here, we're basically saying the opposite then. So H1, we are saying that x following a geometric distribution with parameter of 0.7 is not a suitable model. So this is not a suitable model. Okay. Like so. So that gives us our hypotheses there. So the next thing to do now is to calculate the expected frequencies. So underneath this row here, so this is our row for the observed frequencies. What I'm going to do underneath here is the expected frequencies. So expected here, like so. So to calculate the expected frequencies here, how do we do that? Let me just make a note over here to the right. So expected frequencies. So to calculate the expected frequencies here, this would be E subscript I. So E subscript I here. Well, we do N times by our probability mass function here. So N times by the probability then, our random variable X here, is equal to I. Okay. So N, that is the sum of the observed values. So N in this case then is 200. So I'll make a note here just above our table. So N is equal to 200. So we have 200 then. And then we times that by the PMF here, the probability mass function for a geometric distribution. Don't forget, if you can't remember, the PMF, the probability mass function for a geometric distribution, do just refer to the formula book. Okay. So what I get here then is P, where P in this case is 0.7. I've got 200 times 0.7. We then times that by 1 minus P, so that's going to be 1 minus 0.7, so that's 0.3. And that is to the power then of I minus 1. Okay. Well, 200 times 0.7, that gives us 140 there. So we get 140 bracket 0.3 to the power of I minus 1 there. Okay. So that is how we calculate the expected frequencies here. So for example then, the first expected frequency here, that is E subscript 1. And that would be 140 here. So 140 times by 0.3 to the power of 1 minus 1. Well, my power here then would be 0. So 0.3 to the power of 0 is 1. 140 times 1, and we get 140 there for the first expected frequency. Okay. So my first expected frequency here is 140. I'll do one more, and then what I'll do is I'll just give the rest here, just save a little bit of time. So E2 here, well, that would be 140 times by 0.3 to the power then of 2 minus 1. So 2 minus 1 here. So that's going to be 0.3 to the power of 1 times by 140. So 140 times 0.3, and we get 42 there. Okay. So my next expected frequency here is 42. And what I'll do then is I'll give the next few here. So for the next one then, this would be E3. What I get here is 12.6. For the next one here, so this would be E4. I get 3.78. Now, we do need to be slightly careful here for the very last one. Now, for a geometric distribution, right, we have no upper bound here on K. I know we do for the table here. We define that as 5. But in theory, a geometric distribution could keep going on and on and on, right? So what I say then is this is for K being greater than or equal to 5. So in that case then, to calculate this expected frequency here, so if I skip a few here, this would be for E greater than or equal to 5. Well, in that case then, that's going to be N, which is 200. That's 200 minus then the sum of these remaining expected frequencies here. Okay, so it's 200 minus 140 plus 42 plus 12.6 plus, what's our last one here? 3.78. Okay. So clearly to evaluate this, just use your calculator here. And hopefully what you should find then is you get 1.62. Okay. So we get 1.62 there, like so. So that gives our expected frequencies here. But hopefully you notice straight away we do have a bit of a problem here. And the reason for that is because we have two expected frequencies here which are below 5. And don't forget, when we have expected frequencies below 5, we need to combine to basically ensure that we don't have expected frequencies below 5, right? So in that case then, well, this is 12.6. That's greater than 5, so we don't need to worry about that. This is 3.78, so clearly that's below 5, and this one here is also below 5. However, if I do add these together then, notice now my expected frequency here is going to be greater than 5, right? We get 5.4 here. So in that case then, what I'm going to do here is basically combine these two final columns here. Okay. So what I need then is a new table here. So hopefully you'll be okay with the fact that my table here isn't going to be the neatest. You can, feel free to use a ruler if you want to do it a little bit neater than me. I am doing it freehand. So I've got K here. So what do I get then? Well, I get 1, we get 2, we get 3. And then finally here, because we've combined 4 and 5 here, this is now greater than or equal to 4. So greater than or equal to 4, like so. So I'll put a little line in here just to kind of box that off. Then in the row underneath here, this is the observed values. So observed here. So my first observed value was 130. That won't change. My next observed value was 46. My next one here was 15. And then finally here, for greater than or equal to 4, we're now combining these two columns here. So we now combine the observed as well. So 7 plus 2 gives us an observed value of 9 there. Okay. So we've combined the observed values there. We now need to do the same here for the expected values. So if I do one more row here underneath, again, I do appreciate that this isn't the neatest table here, but I'm sure you can still follow along here. So expected. What do we have here then? I've got 140 to begin with. Again, the first 3 expected frequencies here will not change. So I get 140, 42, and 12.6. So 42 and then 12.6 here. Okay. And then for the next one here, well, we're going to be combining 3.78 and 1.62. So let me just quickly add those together just to make sure I did say it was, what did I say? 5.4. Let me just double check. 3.78 plus 1.62. Yeah, perfect. We get 5.4 there. Okay, that's greater than 5. Perfect. We can now carry on and perform the goodness of fit test here. So don't forget for our chi-squared value here, so that's x squared. What I also need now is the summation then of the observed minus the expected. We square this difference here and we divide by the expected. Okay. So what I now need to do is put basically another row in here, which is a little bit annoying because I've kind of gone over that with my formula here. But I do need another row then to calculate this here. Okay, so the observed minus the expected squared divided by the expected. Okay, I do appreciate that these questions are quite long. They are a little bit tiresome, a little bit tedious, but we'll get there. So let me just quickly rub this off here. Do make a note of that before I do it. So we'll come back to that in a moment. So, like I said then, if I do one more row here, what I now need is the observed minus the expected. We square this here. And then finally, we divide here by the expected. Okay. So for example, I do 130 minus 140. We square that value and then we divide by the expected here of 140. And what I'll do here is I'll give each of these values here 2 free significant figures. So for the first one, I get 0.714. I won't show the calculation for each one. I'll just give you these values. The next one here, you get 0.381. Let's keep going here. So for the next one, again, it would be 15 minus 12.6. Square that and then divide it by the expected of 12.6. You should get 0.457. And then finally here for the very last one, 9 minus 5.4. Square that and divide it by the expected here of 5.4. What you should find then is you get 2.4 here. Okay, so we're getting there now. We're pretty close to the conclusion here. So again, our chi-squared value, x squared here, that is the summation then of these values. So the summation of my observed, so observed minus expected, we square that, and then we divide by the expected here. So let's sum these values here. So I've got 0.714 plus 0.381 plus 0.457 and finally plus 2.4. Okay, just throw that into your calculator here, and if you do that correctly, what you should find then is we get 3.952 there. Okay, again, we're getting closer and closer here. So the last thing that I need here then is my chi-squared family of distributions here. So we need the degrees of freedom. So in this case here, in terms of the degrees of freedom, I have 4 cells of data, right? 1, 2, 3, 4. Obviously, it doesn't matter. I've got these extra rows here underneath. Just kind of obviously the observed value. So 1, 2, 3, 4. We've got 4 cells of data here. We didn't need to estimate P here, so that isn't a constraint. The only constraint then is the total observed frequency. So it's basically going to be 4 minus 1 here for the degrees of freedom. So we have 3 degrees of freedom. I'll make a note of that here. So degrees of freedom is equal to 3. So in that case then, the chi-squared family of distributions, this will be 3 degrees of freedom. And what significance level? 5% here. So 5%. So to evaluate this critical value here, don't forget we need to refer to our formula book. I have also included this snippet here of the formula book if you don't have it to hand. Okay. So for 5%, then we're going to be in this column here. Okay, this 0.05, this corresponds to 5%. And we have 3 degrees of freedom. So we're in this row here, right? So we just keep going until we intersect here with this column, which gives us this value then of 7.815. So 7.815 there. And then finally, we're pretty much there now. All we need to do here is compare our test statistic here, this chi-squared value, 3.952, to this value here of 7.815. So in that case then, 3.952 is less than 7.815. And in that case then, we accept H0 here. So accept H0. So accept H0. And basically here to conclude with, we just say that there is evidence to conclude that this distribution here is a suitable model for a geometric distribution, or it is just a suitable model, right? So there is evidence. There is evidence to suggest or conclude that X following a geometric distribution with parameter of 0.7 there is a suitable model. I'll just put is suitable, okay? Because I'm running out of room a little bit. But there we have it. We finally got there. So I do appreciate that these kind of questions are quite long and there is quite a few different things going on here. But hopefully that explanation, that run through of that practice question, hopefully you found that quite helpful. So there we have it. So that gives us our solution there to this practice question. And that brings us to the end then of this video on goodness of fit test for a geometric distribution.